it is down, so you have some temporary faults. You can talk about the availability of that server. And if it is possible for a steady state measure, so for example, people advertise that their server is available 99.9% of the time, so that is the availability. And that is the steady state availability. Occasionally it may, something may happen and it will go down for a while, but over a sufficiently long period of time, the expected value is availability. And as opposed to this, consider this transaction reliability. Sometimes when we talk about reliability, we are thinking about a specific transaction. So you go to the ATM machine, you want to withdraw some money, so the whole thing is a single transaction. What is the probability that that transaction will happen correctly? It involves a few steps, but the whole thing is a single transaction. And in that case, we can define RT as the probability that a transaction is performed correctly. You can think of transaction reliability as a special case of this. Where the duration, instead of from 0 to t, is equal to the duration, which is long enough to perform the transaction. Now sometimes people use the term reliability without clearly defining what they mean by reliability, so you have to watch out for informal usage of the term reliability. But these are of course formal terms. And then there is a mean time to failure. That we have talked about. And in fact, one of the questions is in the assignment is related to that. So mean time, of course, mean means expected. Expected time, the unit will work without a failure. Mean time to failure, and of course in short it is called MTTF. So, mean time to failure is of course the expected value of time to failure. And there is a related thing. Sometimes people don't distinguish between the two, but the two terms are different. Mean time between failures. And this would be MTTF. So this is the expected time between two successive failures. Now this is a useful measure when failures are temporary. And now we are going to see later on there is a connection between mean time to this, as you would expect, is more useful to describe when failures are permanent. But in some cases there is a relationship between the two. And we are going to take a look at an expression for this. And then there is a term mean time to repair, and that is obviously abbreviated as MTTR. So just like you have a mean time to failure, you have a mean time to repair, and basically expected time it will take before the repair successfully happens. In other words, this is the expected time. During which the unit is not working. Now there is, we want to find out, we want to evaluate some of these, especially MTTF and MTTF. And before we look at some specific example, let us see an expression which is sometimes very convenient for calculating mean time to failure. So basically, there is a connection between mean time to failure and reliability. And I will give you a derivation for this. Now, mean time to failure is, by definition, expected value of time to failure, and that of course is equal to time to failure is that goes between, so t, and here we have ft dt, where this is the density function for time to failure. And now would be convenient if I can replace this by something, and let me sidetrack, and I will sidetrack here, and then I will come back here. Okay, let me do something. So what I want to do is get an expression for ft, and then I will substitute it here. Now notice that definition of reliability is equal to probability that between 0 and t there is no failure. And that, in other words, that is equal to 1 minus probability that there is a failure in 0 to t, right? Okay, and that is equal to 1 minus probability that time to failure is between some t and 0. Okay, and notice that that is equal to 1 minus the distribution function of t. If you want, you can put this here, but that's implied, so I'm not putting that there. So the distribution function, distribution function is the cumulative distribution function. That's why it is also abbreviated as CDF, cumulative. And of course, this is cumulative from 0 to t. And if we take derivative of both sides, we will see that, and let me rearrange it a little bit. I can write, so hence, derivative of ft, I can write as minus times the derivative of rt. Right? And of course, as you know, derivative of the distribution function is the density function. So in other words, and that is what we were looking for here. So let us go ahead and plug in the expression for ft right here and see what happens. So I have t, and let me, we have the minus sign there, and dRt by dt. Okay, so we are getting closer to our aim of getting the expression. Okay, now integration by parts. Okay, how many of you remember how to do integration by parts? You probably remember if you have done it recently. Okay, if not, then you may kind of have to refresh your memory. So using integration by parts, and so you are going to get this result, which is, let me go ahead and erase this because I might need some space there. So by integration by parts, I have this, and I have integral of this, which is just this, and put the limits, plus, and now I have integral of this multiplied by derivative of this. Derivative of this is of course just 1. So integral of this is this. And I'm going to claim that is equal to nothing but okay, do you agree that I can, that this term is 0? It's actually not obvious. And the reason is, take a look at this term here. At 0, it is easy to see that this is 0, right? Because t is 0, and of course this is something between 0 and 1. So the whole thing is 0. But what if when t is equal to infinity, your RT is probably approaching 0, and this is infinity. Now what is 0 multiplied by infinity?
0.
And that means that it depends on what specific expression it is. Now notice that, and here let me sidetrack a little bit. This is of this type, x e raised to minus x. Because reliability is often e raised to minus something. And you can show that this tends to 0 as x tends to infinity. And hence, this TRT approaches 0 as t approaches infinity. So this is indeed 0, and hence we get this nice looking expression, which is quite useful. So it can save you a lot of work. The reason is that, let us say you have obtained an expression for reliability, and now you want to calculate MTTF, then all you need to do is to plug in the expression for reliability here, and solve it, and you get your expression for MTTF. So it's a convenient expression. This is one of the results worth remembering. Okay, so let's come back to this here. And let us explore the connection between MTTF and MTBF. Let's consider failures with Malaiya. Okay. Time between failures is equal to time to repair.